welcome. My name is Peter Frey. I'm with Mentor Graphics. I'm an HLS technologist, so I'm working very closely with the Synthesizable subset. Today I'm going to give a little update what happened since last year and where is the technology going. The standard is intended to provide the designer with an HLS tool or tool set, which is allowing to take the model, the SystemC model, from one tool to another tool to allow basically exchanging the different HLS tools or having basically allowing to build an ecosystem for the synthesizable subset or synthesis with starting from SystemC. The standard was approved last March. It covers the C++ and the SystemC supported and unsupported language constructs. And it is basically 100% focused on the syntax. So some of the things I'm going to talk is a little dry because syntax of the language will be addressed. But I try to present it here with an example. And this is basically a simple SE module description. And the first thing, depending on how you use SystemC before, for the synthesizing subset, all inter-process or inter-module communication channels need to be based on signals. So you cannot use any of the TLM structures and so on, because the synthesis tool would have to create the protocol around it. And for SystemC or for synthesis today, you will have to define it like in the model itself. So as you can see, you have SE-ins and SE-outs. These are the basic channels, and they are defined with different data types. And basically, most C and C++ data types are supported. So I'm saying most because for C++, basically double and float are not supported, especially also the behavior underneath it. And they're defined between map.h and so on, and the synthesis tool wouldn't know how you want to implement your divider, right? So the synthesis tool will need to have an explicit definition of all of it. But integers and long, all integer types are basically supported. And if we go further into the different modeling structures, or let's say with the data types first a little bit. On the data types, you support all the SystemC types from SE fixed points, SE ins, SE big ins, all of them. The fast types are supported as well for synthesis. And in general, you can map all of them into, any of your models you're writing with these data types will be automatically synthesizable. There are a couple of exceptions. As I said, math.h library support is one of the parts. You will have to look into more detail if you use them on integer data types. Other SystemC data types or SystemC function like range, you have limitations that the range needs to be increasing. You have the first index need to be lower than the upper index. Similar, you will have to support divisions and multiply and modulos, as I said. You will have to provide a definition for it because there are many different implementations for hardware. On SystemC data types, there's other modeling constructs, as I said, TLM is not supporting, but you're also using potentially SE events, all the higher level abstractions. They cannot be used for modeling your behavior. These are the main limitations, but if you can look at the module here, you can define your hierarchy with SE modules. You can instantiate submodules. I don't have an example here. You can have your local variables like in any C class. The only difference for synthesis is that these modules or these variables can only be accessed by one of the processes. Because otherwise, even in simulation, you have race conditions if you allow them to be accessed by different processes. So that is limited. On the modeling constructs themselves, if you have here in the constructor, you can instantiate different threads. You can instantiate C threads, or threads, and SE methods. All of them are supported. And the only caution I would give with SE methods is that SE methods are very low-level modules. So for high-level synthesis, if you define it, you're basically defining cycle-by-cycle behavior, so you will not get the same behavior as if you would use SE threads, where basically high-level synthesis is expanding your design. You should be all familiar with setting the clocks and setting the reset, and with respect to polarity as well. In the process behavior, if you're coming from the C++ background, you're used to initialize your variables all in the constructor. If you go into synthesis, this will have to be covered in the reset behavior. And the reset behavior is basically everything from the start of the process all the way to the first wait statement in your process description. So the A, C, val, and your signal outputs, this is considered the reset behavior. Everything below is then the normal process. The process with respect to SystemC synthesis will have to have infinite loop in it. You cannot use any of the dynamic behavior constructs of SystemC. You cannot create and destroy, kill any of the process commands SystemC supports. You cannot use. The model will have to be statically determinable. If you then go into the behavior down there, this is in the while one loop. This can have any amount of different wait statements in there, but only two kinds of waits are supported. Wait and wait integer down there. You can basically say I want to wait 1 clock cycle, or you can wait n clock cycles, giving some latency information to your model from your behavioral description. Important is also that you will have to define your protocols, as I showed down here in the last 7 lines. This is where you have to model your protocols based on signal toggling. With respect to the synthesizable subset, I mean, you can wrap them in classes. All of that is supported in the normal C++ modeling, but you cannot use any kind of more abstract protocol definition. Yeah, I already mentioned the math.h support is not there. Coming back to the operations and the support, so usually you will not find any issues with respect to taking your model and taking it down into a synthesizable model with respect to the supported operators. As I said, there is just a couple of limitations or things you need to be aware, and usually your tools warn you if you use any of the non-synthesizable constructs. One more thing on the slide before. Here you would also define, if you go in a higher level, you would be able to use SC FIFOs, SC event queues, SC semaphores, any of these abstract modeling concepts. They're not supported in the high level, the synthesizable subset. So that's basically just an overview how you can model. And now what's going on in the community with respect to high level synthesis. Basically there are 5 areas which we are aware or we need to look at. One is newer language constructs. C++ 11, C++ 14 is out there. These are new language constructs which people use in their models, and the synthesizable subset committee is looking into can we support them and how can they be supported. Similar enhanced bit accurate data type modeling, and we will go into more detail on that, is SystemC provides the bigins, the SC-ints, all of these data types, but they have a simulation cost today with respect to SystemC. And so we are looking into can we provide better data types there. Protocol libraries, I will present a little example on where's protocol definitions, as you have to use them explicitly in your model description. That is falling apart when it comes to synthesis. So we need to look into how can we do this in a better fashion. Similar latency constraints and common synthesis control structures. So let's start by looking at the C++ 11 construct. This is currently in the active discussion in the synthesis working group. And so we are basically looking at auto and decal type, the C++ construct where you no longer have to define what is the return type as long as it can be clearly identified from the model. This can be synthesizable, so we are trying to support this. Similar constant expression, that's quite powerful with respect to high-level synthesis, as you will have to have your model statically determinable, and if you have a constant, like in this Fahrenheit 20, you would exactly know what's the result in Celsius. So today you would have to do the math separately and put it into the code. This can be supported by high-level synthesis right away. Similar template aliasing, this is just syntax, right? It allows you to write it easier. It doesn't change any of the basic requirement for high-level synthesis that the design needs to be statically determinable. Variative templates, same thing. So you have multiple arguments. This doesn't really change what the struct tuples in this case is going to look like. It simply allows you to have different types there. Initialize a list can be simply a front-end issue from a synthesis perspective. And lambda functions. basically having unnamed functions supported. From a synthesis perspective, this is still needs to be burning down to a fixed function or any C++ function, and so this can be supported from a synthesis perspective. More interesting it becomes with bit accurate data types. Mentor has released the algorithmic data types. It's a library of bit accurate data types, and it's publicly available, licensed under Apache 2.0. It is used from many SystemC modelers due to the capability of allowing arbitrary length. You don't need to use big int or uint or ubig int. It has a precise and a consistent definition of the semantics, and it has a big advantage over simulation speed. So Accelera is actually has created the SystemC data type working group, which is trying to take in some of the capabilities of the algorithmic data types and provide a more efficient SystemC simulation standard. So this is SystemC interface and latency modeling. Basically what is in the orange boxes is a simple protocol definition, and in general you have your data right and your valid setting to true, and then you're waiting until the data is read. So you have a simple valid ready high protocol here, and you do the same on the receiving side with the ready signal, and you get a full protocol, a handshaking protocol. Now the problem is when it comes to synthesis takes wait statement, right? The whole purpose of synthesis is actually to add latency and make the design be schedulable and implementable. And so in general, SystemC or synthesis is adding wait statements to make your design implementable. The problem comes here with respect to interfaces. We will potentially add waits anywhere in the model. I mean, here I just added, for example, the black wait statements here, and they can be of arbitrary length. Some might be a single wait, might be two waits, multiple cycle, based on latency requirements. The problem is, right, this is going to break your protocol, and so we are aware that the SystemC synthesizable subset needs to provide some standard means of defining regions of stability, basically not adding any kind of extra latency or delay. And so this is something we need to look at. For today, it's really that the different tools provide their individual solutions to limit time extension or latency extension. Common synthesis control structures. What high-level synthesis is doing, right, is you take the function like this max function here. It has an accumulator and adding up the data multiplied by the coefficients, and then returns the accumulation. This can be implemented in different ways, right? You can either have multi-cycle implementation with one multiplier and one adder, and then have a single register and a multi-cycle execution, or you're fully parallelizing it and you're doing the multiply and the add with more hardware and a single register and a single cycle. So you're trading off parallelism versus area. The designer in general knows what he wants to implement, and especially in the small examples like this, the designer would like to write inside of their code statements of what to do with this loop. So in this case, the lower part is unrolling the loop, the upper part is just leaving the loop as it is. And synthesizable subset doesn't define any construct to do that, or any pragma, for example, to allow this code to be simulated as well as synthesized in a specific manner with different tools. So we are aware that this needs to be addressed, and we are looking to have this implemented moving forward. In conclusion, the SystemC synthesizable subset clearly defines the SystemC C++ syntax, which any compliant tool needs to support, but we are very much aware that there is more to be done and extra constructs to address that. We need to go further to define these things, potentially have extra libraries or protocol libraries which are shared across the full. This is all under consideration. The good thing is this is a very active community. Standardization effort is going on. As I said, the C++ 11 constructs, this is currently under consideration. And the goal is really to ease full HLS SystemC adoption.
I'm Trevor Wieman. I chair the Configuration Control and Inspection Working Group. I'm going to talk about the configuration standard and provide a tutorial, but before I do that, I did want to slip in a quick update here on the 2.3.2 kernel update. You can download 2.3.2 and take it for a drive. It's going to do a 3-month public review. And this is a maintenance release with some new features. It is licensed under Apache 2, which all of the SystemC works now are. A few highlights of the 2.3.2 release. It now does have a foundation for enabling C++ 11 and 14. The details of that actually you can find a paper for from DVCon Europe. And this is about providing the ability to start opting in C++ 11 and 14 capabilities into the standard language in a way that, of course, maintains backwards compatibility for users who are not able to move to the newer compilers yet. It also has a global name registry added. This was useful for us in creating the configuration standard, where we wanted to try to make sure that we didn't have conflicting names between different domains. So, for example, having a configuration parameter that had the exact same name as a SE object or an SE module. So this registry helps us to avoid that. There are some new base classes for the socket and the signal that let you get at some generic things without having to know the exact templated type. So, for example, if you want to know that a socket has been accessed, you can do that now with this base class, and you don't have to know the particular protocol specifics of that particular socket. There's updated compiler and platform support. We now have improved support for dynamic libraries on Windows, and there's support now for CMake. That's considered experimental at this point, so this is a particular area where we're interested in feedback. Are you interested in having this one build system that lets you work from one set of build instructions both on Linux and Windows pretty seamlessly? And then there's a number of bug fixes and cleanups. There's a README there with the download that will give you all the details. So let's talk about the configuration standard. First, some acknowledgments. So this tutorial has its origins back to something that Doulos started for us, and that it's been picked up and adapted and improved upon based upon the evolving standard by Ericsson and Greensox. And so it brings us to where we are today with this set of materials, so appreciation to those folks that did that work. Also, the note here on the bottom, we want to recognize that Ericsson has provided significant resource into this activity to help us accelerate the work that's being done here on the standard. So we wouldn't be where we are today without the support from Ericsson that's helped us to accelerate this. Okay, so a little bit of a background here. The Configuration Control and Inspection Working Group, if we jump all the way down to the bottom here, it's about being able to connect your models with your tools and do that in a standard way so that you can bring models from other organizations and put them into your environment, work with your tools, and still take full advantage of the tool capability. So up at the top, we've got tool use cases, wanting to do things like system-level debug, analysis, authoring, checkpointing your simulation, doing reverse simulation, all the kinds of cool things that people are doing today in their tools. That requires some ability to go in and take a look at the models. So if we look at the very bottom row here, there's information in the models about how the model is configured, internal state, data like performance information or power data or statistical information, and some support for built-in debug capability. So how do we get from the top to the bottom? That's what we're doing. We're trying to create these standard interfaces in the middle that will allow us to achieve this level of interoperability. So far, this working group is focused over there in that far left-hand corner, where we are creating a standard parameter that allows us this path to configure our models from any standards compliant tool. Okay, so that sets the stage. So where we are now with configuration, we can think about a standard or a typical SoC today where you've got some processors and you've got a memory subsystem and you've got a bunch of IPs that you get from a variety of different sources that provide acceleration of particular functions and coprocessors and IOs and all kinds of things. And we want to be able to configure all of those models in a consistent way. So what are we talking about when we say configuration? So here's some examples. What's the system clock speed? How many cores am I instantiating in this particular simulation? What's the size of my memory, my cache, etc.? What's the width of my address and data buses? Which subsystems or IPs do I want to disable for this particular simulation? Because maybe I want to focus elsewhere in the system and I want to be able to increase my throughput by turning some of the IPs off. How do I configure the address maps in my system? How can I provide the file name that I want to use as a software image. And then there's some level of debug and control that we get today just with parameters. So at a module level, am I turning my logging on? And to what level of detail? And am I tracing through a TLM socket, for example? Those things can be done as well with parameters. So we're getting a start on some of the control aspects of our charter, but really the focus is on configuration. And we realize that today there aren't too many people out there trying to get all of this done with simple C++ data types. They have their own configuration parameter classes. So what we really need here is we really need a standard that lets people do this in the same way so that the tools can interact with the models seamlessly, and that you can do it, of course, all without recompiling your source code. So that's what we're going after. To give you now a little bit of a tutorial on the specifics of the standard here, the CCI, or Configuration Control and Inspection standards, are going to require SystemC, of course. They work best with 232 because of this central naming registry. They are compatible with 231. It won't give you quite as good a check when you're looking at name collisions, but it otherwise works completely functionally. We do have a common header file, CCI configuration, that you can include to get you access to all the interfaces that are included in the standard. And everything is buried down inside of a CCI namespace. That kind of is the basics here of the standard. Wanted to just give a little bit of a quick intro to set the stage for what we're going to be seeing today. I've put together this pyramid here illustrating what pieces of the standard over here are relevant, and then for what particular use case and how common they are done. So at the very bottom here, this is, I want to put a configuration parameter into my module to allow parameterization of it. That uses the parameter class. That's what will get done by lots of people, and that's kind of the foundation. Everything else builds on that. So the next thing up here in terms of how commonly things are used is intermodule configuration. So I'm in source code here, I'm within one module, but I know about a parameter in another module, and I want to be able to go get access to that parameter and then interact with it. And that requires for us this notion of a broker. A broker helps us get access to other parameters, and a handle. So if I don't own the parameter, but I want to be able to interact with it, then I get a parameter handle. The next level up here is being able to respond to changes to the parameter value. So if I own a parameter and whenever it changes, I need to do something about it immediately. I don't want to just periodically check to see if something has happened and respond. I want to respond immediately. We have callbacks in place for that. And we have this notion of a private broker that allows you to control whether your parameters are accessible outside of your IP or not. And so at the point that you're starting to package your simulation and putting together subsystems, we introduce the notion of a private broker. And then up at the next level, we've got support for custom types. So there's natural support for typical types included within the configuration parameter, but there's the ability to support any arbitrary type. And that's something that probably a fewer number of people are going to be doing at an infrastructure level. And then finally up at the very top is, how does a typical tool interact with the user? The user supplies a configuration value. It's got some strings representing parameter names and some strings representing parameter values, and you want the tool to pick that up and push it into your parameter. So that gets taken care of here with originator, which has to do with keeping track of where the values for a parameter are coming from, and the CCI value, which allows you to interact with a parameter without actually knowing its underlying type. So we'll talk about more about this variant type, but it's very useful at the tool level, and it's not only used getting the configuration file values into your parameters, but then also getting parameter information out of the simulation and presented to the user. So telling the user the name of the parameter, the values of the parameter, the description of the parameter, all of that information can be taken care of as well. And again, that's done in a way that you don't have to know about the type of the parameter through the CCI value mechanism. So we'll talk about all of these, and you can kind of maybe pay more or less attention depending upon the area that you're interested in. Okay, so some of the most fundamental key concepts that we have here within the standard are the parameter. That's pretty logical. So the parameter, again, has a name and a value. It's this instance of CCI param with a templated type. It gets registered with a broker at construction. We'll talk a little bit about broker next, but parameters belong to a particular broker. And I've alluded to the fact that there's a couple of different ways to interact with the values of a parameter. So there's this untyped notion that allows you to both get information out without knowing the type of the parameter, and also to update the value of the parameter without knowing its type. And so this variant type we'll talk much more about, but it is compatible with the JavaScript object notation, and it's really there, like I talked about, to allow the tool to do the things that it wants to do when doing a real-time introspection of the parameter. And then, of course, there's a typed interface as well that allows you to get at the values of the parameter when you know the actual type that it's been instantiated with. We'll get into much more of that. It'll become more clear as we work our way through the slides. So the next is the broker. The broker manages access to the parameters that it manages. It's used both by models and by infrastructure and tools. So I mentioned the fact that one model might want to go grab the parameter of another module. It talks to the broker to do that. And I also talked about how a tool might pick up a configuration file value and push it down into a parameter. Again, in order to find that parameter by name, it will use a broker. So there's two kinds of brokers in this system. There's one that is the one everybody knows and loves when you start working with a standard. That's the global broker. It's public. It's always there. It's the thing that manages parameters by default. And then there's the ability to come in and introduce a private broker where you want to restrict access to your configuration information. And any number of private brokers can also exist within a simulation. Okay, so I'm going to talk a little bit here from a pretty high-level view about how these things interact together. And so let me start down here with a parameter owner. This is typically a SystemC module. The modules will create instances of parameters to parameterize the module. And when they get created, they're going to do this registration with the broker. And then the broker is going to optionally take initial values that have been provided to it and use them to provide the starting point value of the parameter. Once we've got parameters in the system and we've gone through elaboration and the brokers are in place, the parameter, of course, the parameter owner can just interact with the parameter as if it were a plain old data type. If it's an integer parameter, it's a lot like reading and writing an integer. If you get a handle, so we talked about being able to go out to the broker and do a lookup on a parameter name and you get back a handle. This can be done module to module or by the tool or by anything else. If you get a typed handle, then you can access this parameter the same way that the owner does, effectively. And if you don't know the type of the parameter, you can do an untyped access. You can still interact with the parameter, but you use this variant type, this CCI value that we'll be talking about. So this gives a 30,000-foot view of how all of these key components play together. So let me talk a little bit about this initial value concept and how the parameter gets its starting point value. So I showed the path that had the ability to go into a broker and supply an initial value. And again, this can come from a configuration file. It can come from within code. It can come from anywhere. But it's the ability to go to the broker pre-elaboration and let the broker know that for a particular parameter name, you've got a value that you want to supply as a starting point. So here we go. We're looking at a little bit of syntax here for the standard. We're going to go to the current broker. We're going to set an initial CCI value for a particular parameter. And we're giving it a value here. We're giving it a value of 10. Another way the parameter can get its starting point value is through the constructor argument. So here we've got a parameter, CCI param. It's templated on a value type of integer. We're giving it a name, myParam, a variable name. And its string name within the naming hierarchy is param_name, and we're providing here an integer value of 42. So this is the parameter owner. It's the module that created the parameter. It's constructing it, and it's giving it a value. Now, if the initial value exists in the broker, it has precedence. So this is everything that you would know about this parameter as the creator of the module, but you don't always know how this thing is going to get instantiated and used. And the idea is that somebody else, when they need to, can use the broker to come in and bring another value that makes more sense in the particular instantiation of your model. So in this case, since we did have the initial value being provided to the broker, when we come in here and we create this parameter and then access its value, so myParam get value, we're going to see that it would take on the value that came from the broker. Next, we're going to talk a little bit about this variant type. So again, there's two ways to get at the parameter values. This untyped thing uses the variant type CCI value. Complex types can be emulated as a collection of primitive types. So if you've got a real and a string, you can put them together in a list. It's a list with a real and a string. item in it, that represents the data that you've got, but I don't have to know the actual C++ type of your parameter's value. There is built-in support for C++ and SystemC types, and it, as I had mentioned, is extensible to support user-defined types. You provide the ability to pack things in and out of your type, and you're off and running here. And again, this is really critically important for tool enable. So we talked about being able to take values from an ASCII configuration file, where of course you don't know anything other than a string representation of the value. As long as that's in an appropriate format, it can be pushed down in through the CCI value mechanism into your parameter, and the code that's doing that work, the tool or the infrastructure, doesn't have to know about the type of your parameter. And the same goes in the other direction. If we want to take information out of the parameter and present it to the user, some kind of complex structure of a type that's represented in this case by a number of primitive data types, we can pick those bits and pieces out and present them in a way that they make sense to the user, all without actually knowing that particular complex structure that was used to template the configuration parameter. And then of course there's the typed interface, and that's using the template instantiation type. It's more direct, it's probably more intuitive, and it's certainly more efficient. So when you know the type of the parameter, that's what you're going to fall back on and probably use the most. It's just when you're working more in an introspective way and you're just trying to find out that there's a parameter with this name and then wanting to get at the information that you need to use this untyped path. So this CCI value mechanism, we've been talking about how there's value in that above and beyond the configuration space within the core language. You can imagine that, for example, you want to be able to show in your tool the value of a complex type that's used to instantiate an SC signal. The same thing could be used. If we used a variant type there, then tools could pick up and display for you in a reasonable way the contents of your signal without actually having to know the particular custom type that's been defined in C++ to carry that payload. So it's anticipated that as this gets road tested a little bit, it would get renamed as SC variant and moved into the core language. So originator, I note here, and I mentioned earlier that the origin of the parameter's value is always known. So one of the things that was a key requirement in putting together the standard was that when you went out to a parameter and you asked it what its current value is, that you also could know where that value came from for traceability and debug purposes. So at any point in time, you can ask the parameter what's your value and where did it come from, and it will tell you where it came from. So we have this originator class that helps us to track this information. And within the SystemC module hierarchy, the originator is determined automatically based upon the name of the module. So if I create a parameter within a module and it has a name that looks like this, then an originator automatically comes into existence to reflect exactly that module's name. And now then, if the module itself updates the parameter value and you ask subsequently the parameter, where did your value come from, it will tell you that it came from this module. And you'll know that, well, the module that owned the parameter is the last thing that set this particular value. Now, originators can be set explicitly as well, and if you're outside of the SystemC module hierarchy and you have no reference point, then you're actually required to explicitly set the originator name. And you can do some things like, for example, indicate the name of a configuration file. So here we've got a platform basic configuration.cfg file to represent a file that had some configuration values that got read in the beginning and loaded into the parameters of the system as a starting point. And so now if I go to the parameter and ask it, where did your value come from, and you see this, you know, okay, this thing hasn't changed since it was loaded at the beginning of the simulation, and if I want to go run down or possibly change what that value is, I can go to this file and open it up, look for that parameter name, and take care of it. So good traceability. And then more generic things. So if you're in your tool and on the fly you've asked the tool, hey, I wanted to go in and change the value of this particular parameter, then the originator probably is used to reflect the name of the tool or something like the user or your username or something to that effect. So now when you go in and you ask the parameter who set this value, you can find out that, you know, basically you or the person that was running the simulation, if it's a batch job, that it was done interactively, and that's where the value came from. So it's really important to note that all this originator stuff is there to satisfy this critical requirement of making sure that you always know where the value came from. but it's really handled all behind the scenes. So as a programmer, as a modeler, you're not going to deal with originators very often. Now, if you're the person that's working on the infrastructure and you're processing configuration files, or you're working in a tool and you're setting up interactive parameter updates through a tool, then you're going to want to take care of originators appropriately. But otherwise, these are just things that help you to determine the source of the value, but that don't really come into your day-to-day work at all. Okay, parameter handles. So a parameter handle gets returned by a broker when you do a name-based lookup. So if you go out and you go to your current broker and you say, I want to look up a parameter with this name, then it will give you a handle. The handle provides an interface very much as if you had created the parameter yourself. That interface is very consistent. It's possible that the handle has some restrictions with it, depending upon the policies of the broker. And the handle informs the parameter of the originator when the value is updated. So I mentioned that this is all kind of behind the scenes, but what happens when you go out and you do a lookup and you get a handle, the handle actually maintains your originator information inside of it. And now then, anytime you go in and you do a set value through your handle, it remembers who you are, and then it updates this traceability bit of information that's within the parameter to track where the values are coming from. And the handles, again, are available, as is everything here in the standard, in this untyped and typed forms. And we've got down here the class names, so CCI param untyped handle and CCI param typed handle. The first one uses this CCI value variant type, and the second one uses this type that was the same as used to instantiate the parameter itself. Okay, so a little bit more about handles and how they work and how they're structured. What I've got drawn here in this yellow block is things that are included in the standard. Within the standard, we have the standard CCI parameter interface, so that's how you interact with the parameter. We have this CCI param untyped class. That's a way of looking at a parameter. Now, all of the concrete parameters are typed. So when you are in your module and you create a new parameter, you must give it a type. But you can still look at it in an untyped way depending upon your particular view of this parameter. So that's all provided by the standard. That's all the parameter hierarchy. And then over here we've got the handles. So we've got an untyped handle, and then as a subclass of untyped handle is the typed handle. It's a superset of everything that you can do here. And the handles basically are redirecting the interface that's similar, as we mentioned, to the parameter itself, redirecting those calls into the actual parameter through an association with a actual parameter. Now, over here on the far left, we've got a customer parameter implementation. So we've gone out of our way here to make sure that the path to being compliant with the CCI standard is fairly seamless and uncostly. So if you've got your own legacy parameter, you can conform to the CCI parameter interface. There's some requirements like registering at construction with a broker. But then once you've satisfied this interface, you can play in the system equally well as the parameters that come with the standard itself. So now if I go out to a broker, it's already been registered, I do a lookup, I get a handle, it can be untyped or typed, I get a handle to your legacy parameter, I can interact with it through the handle, and to me as the handle consumer, there's no difference from the actual standard parameters. Now over time we certainly encourage and hope that people will start using the standard parameters, but there is this transition path that allows you to very quickly become compatible with the CCI system and continue to use your existing parameters and not have to change model source code that you have today. So a couple of convenience things. We have a lot of these big long names, and so we really put some thought into, well, can we make life a little bit easier? And we decided that, looking at use cases in our examples, that when it comes to the handle, the most common thing you're going to do is grab an untyped handle. And so then the CCI param untyped handle gets typed def to just CCI param handle. So now we can just talk about CCI param handle, and that always means to us an untyped form. And then with the parameter itself, the CCI param, like I said here, when you create an instance of a parameter, it's always the typed form. So we make life a little bit easier, and we just call that CCI param. It is templated, so you give it the value type when you create those parameters. But you don't have to type out the big long name here. Just a little bit of convenience. Next, just a little bit of a feel for, now that we saw that picture and it talked a little bit about what's in the yellow box and what comes with the standard and what's not in the standard. To back that up, but to reinforce that, what's in the standard is the parameter and the broker interface. So those key interfaces are part of the standard. The default implementation of the CCI param, and of course that includes that hierarchy which involved the untyped param as well. The originator and the handle classes are included in the standard, and all these things are implemented in the proof of concept. And the callback infrastructure, we'll talk a little bit about callbacks in some upcoming slides, and this variant type, the CCI value. So those are all parts of the standard, and those all are included in the proof of concept implementation. Now what you'll get from your tool vendor or from your infrastructure are the broker, possibly private brokers, and any support for a particular configuration file format. So one of the things that we kicked around in the beginning was, since everybody takes configuration files and feeds them into simulations, can we standardize that? And we quickly realized that everybody kind of has their own that they have some affinity for, and that we don't want to try to encroach on that. So you do this with your particular infrastructure or your tool, but then the way that you take those values and put them into the broker so that the parameter can pick them up is where the standard kicks in. So this is a parameter owner module. So SC module simple IP is the name that we've given it. We're plunking down a parameter here. So it's a CCI param. It's going to have an integer value, and we're just calling it int param. Parameters are typically, and we recommend putting them as private members. This forces brokered access. So we really want to make sure that if somebody else is getting at your parameter, that it's being done through a broker, and that the originator information is being tracked, and that any access restrictions are being adhered to. So as long as you put them into the private region of your C++ module class, then everything is good. Next in the constructor here, we see the construction of the parameter itself. So we're giving it a name and we're giving it a value. So our int param is going to have an integer 0 value to begin with. We do require that default values are supplied with the constructor. There are an overloaded number of constructors that let you specify some additional information, and we can see here that one of the things that you can do either as a constructor argument or through a setter function is to set the description. So you can provide a description that then gets relayed through the tool to the user. So what is the purpose of this parameter, and or what are the constraints on its values? Anything that's useful to somebody using that parameter, you can help by providing through this description mechanism. Now then, once that much is done, then anywhere within the body of your module, you can reference this parameter. Here we're reading the value, just as if it were an integer for the most part. So some of the interface for accessing parameter values. When the value type is known, you can call setValue, getValue. That's this templated interface. And again, it works on common C++ types, SystemC data types, and is extensible to supporting user-defined types. And then when you don't know the type of the parameter, you come in and you use CCI value, this variant type, and you can do things like set CCI value, and you give it the details of this collection of primitive types that let you update the parameter's value. And if the conversion fails in the process of attempting to update the value, then you'll get an error as a result, and the value won't be impacted. You can also do a get CCI value, and so we've kind of tried to fairly consistently through the collection of interfaces indicate when things are either the actual type with just set value, get value, or with the invariant type by putting in CCI value into the name. So set CCI value, get CCI value. Okay, so let's look at a little bit of this. So this is looking up a parameter through the broker. In this case, we've got a module, we're calling it configurator. It's just a generic name that we came up with that means an entity that's doing some configuration of the system. We're declaring a broker here of type broker handle. So CCI broker handle, we're calling it mbroker. And now then in the constructor for this module, we're coming in and we're initializing that just as get CCI broker. So in the coming slides, you'll see that there's a system in place for determining which broker reigns over which parts of the system. And then as a user of the CCI interface, you only really have to ever know that you can always get at your broker by calling get broker. So getBroker does the right thing and gives you the broker that reigns over your particular module. And now that you've got a broker handle, the first thing that you want to do, as with all the handles in the system, is check to ensure that it's valid. So if something went wrong, or there's no awareness of your module within the CCI system, something's pretty wrong, but you can check that everything is okay by checking the status of your handle. So as long as broker handle is valid, you're good to go. So then, continuation of this example, we've got a process now within our configurator, and the first thing that we're doing is we're just creating a temporary variable to hold the name of a parameter. And this looks like a typical hierarchical name in SystemC. Top, some sim-IP, and some int param. We saw int params being declared before and what they look like. And now then I'm going to come down here and I'm going to create a CCI parameter handle. And by default, recall that that's the untyped form. I'm going to call this variable int param handle. I'm going to go ask the broker to get a handle, and I'm going to give it this name. So just put it here in a temporary variable for convenience. And the first thing I do with my handle is I check to make sure that it's valid. So if I didn't have authority to see that parameter, my handle will not be valid. If I mistyped the name and no such parameter exists, my handle will not be valid. So I have to just do a sanity check here the very first thing and make sure that I have a valid parameter handle, and then I'm able to proceed. And in this case, all we're doing is we're coming into the handle and we're doing a get CCI value. We're putting it into a temporary variable named value, and we're incrementing that value, and we're coming and we're putting that value back into the parameter here using set CCI value. So here we didn't necessarily know. Now, based on variable names and based on our prior example, we really knew that it was an integer type, but nothing here is requiring that we syntactically specify the type of that parameter. Now, of course, yes, we had to know here, we had to have some idea that whatever the type is, that it's mathematic and that it can be incremented, but beyond that, there's no requirement to know more detail about the type of the parameter. Next is the parameter mutability. So parameters by default can be changed anywhere, anytime, and that's the default setting. So if we come down here and we look at the interface for instantiating a parameter, we've seen CCI param int before. There's an additional template argument for the mutability, and it by default is CCI mutable, which means that you can change it anywhere, anytime. Parameters also can be entirely immutable, which means they're constant, so you can give them a value in the beginning, but once they're set, they can never be changed. Or they can be immutable after elaboration. So we've got the enum down here to represent the different template instantiation mutability options. And the elaboration parameters are typically used to configure the simulation structure. So if you are creating, we saw back in the beginning a picture of possible parameters in a typical SOC, and one of the things that we said was we might have a parameter indicating the number of processors that we're going to instantiate. Of course, you want to do that during elaboration. If you do that in the middle of the simulation, it's not going to be a very good thing. So we can indicate that by using this elaboration time parameter. If you attempt to change it after simulation starts, then you get a warning and it has no effect. I already talked a little bit about the description, so here's a little bit more about it in an example. So I can have a parameter and say set the description to say that this is the clock frequency parameter. And it's intended to explain the purpose and the use of the parameter to the simulation user. And again, it can be supplied as an argument to the constructor or with a dedicated setter. The parameters also have an array of meta information that's there to allow you to attach additional information in a very free-form style. Here's an example. My parameter, I'm going to add metadata, and it's a map, so I'm going to use units as the key, and then I'm indicating here that in a pair that we've got V as to represent voltage as my units of the value, and we can get the metadata out as well, and you can go parse through the returned array of meta information to get at those details. So this just allows, there's nothing standard or constrained about what you can put here. It just allows you the flexibility to put information into and associate it with your parameter to provide any purpose whatsoever for an entity like a tool that wants to go in and look at additional information about your parameter. Over time, there may be some of this metadata that gets standardized. We can imagine that units would be one of those things that we might want to standardize. We can also imagine lots of other use cases for this kind of a metadata. But for now, it's all very free-form. Okay, next, a little bit about private brokers. And I've got a picture on the next slide to kind of illustrate this. So each parameter gets registered with a single broker. We've talked about that. When the parameter gets constructed, it has to go to the reigning broker and report to that broker and say, hey, I'm alive, and here I am. The broker is then going to manage all accesses to that parameter. Private brokers are assigned to a module hierarchy. From that point forward, then, any of the parameters within that hierarchy are registered with that private broker by default. Now, any parameter there can still be explicitly registered with a different broker, with a global broker or yet another private broker. That can be done explicitly. But implicitly, by default, everything that gets created within that hierarchy is going to be associated with the private broker. So private brokers are undiscoverable outside of their associated module hierarchy. So if you are within that hierarchy and you do the infamous get broker call, then you're going to get the private broker. But if you're outside of the reign of that broker, there's no way for you to go find out what private brokers are in the system because they're supposed to be private. So this is not discoverable even by the tool. So if you're working with a tool and you have chosen or you have IP that you've received that has a private broker in place, it's really hands-off to you. You're not going to know about it. So what the net effect of that is then that parameters are inaccessible from outside of that hierarchy. You can't get at the broker. The broker is the way to get at parameters, so you can't get at the parameters. And the private brokers can facilitate encapsulation of IP configuration. And so, for example, you could have a configurator, something that takes code and sets all the predefined values for your parameters and gets compiled into your library and then associated with the private broker, and then all bundled together, the private broker, the configurator, and your models, and delivered to somebody else. And then that's all together and treated as a black box, and you can't see and have any visibility into what's going on with that configuration information. So there's no file that is involved here. It's code, in this case, that's providing this level of encapsulation and allows you some level of protection of how your IP is configured when that's required. So let's look at that picture then. This is an example of creating a module called Subsystem A, and within the Subsystem A we're doing a CCI register broker, and we're giving it my private broker. Now, where my private broker comes from, there's of course no hints or suggestion. It's something that's private to you. You've come up with a broker, you've registered it with the system. Now then, in our picture below, the kind of pink coloring indicates everything that my private broker has reign over. And we can see down here that parameters that are managed by my private broker are all the parameters in Subsystem A or in IPQ or in IPR. And then everything else within the system, parameters that might be in top or Subsystem Z or IPW or IPX, those are all still managed by the global broker. So then for robustness reasons, only the module itself can specify the broker. It would be kind of crazy if somebody else could indicate that you were going to use a private broker. So only the module can do that. And then callbacks. There's two classes of callbacks in the standard. One is to deal with parameter value changes. There's a set of read callbacks, post-read and pre-read, and a set of write callbacks, pre-write, post-write. And then there's also a set of callbacks at the broker level that inform you about parameters being created and destroyed. So if you want to know when any parameter is created for a particular broker, or when a parameter gets destroyed under reign of a particular broker, you can ask for callbacks and be informed about that. So kind of the general interface here for the callbacks is that they have a payload that we'll see on the next slide carries the kind of information that you would expect in these kinds of callbacks. And you can get a typed or an untyped form depending upon what you know about the parameter that you're establishing a callback for. And we do have compatibility with C++ lambdas and function objects. And this implementation of the callback mechanism is provided by the standard. And the final note down here at the bottom is that this is another one of those areas where it seemed like what we were putting together here has applicability beyond the CCI domain. There are some, for example, callbacks within UVM-SystemC, and so in order to look at having some consistency, there's this mindset that we probably want to take the callback mechanism itself and promote it up to the language working group level, and then try to come up with something that we can all use in a consistent manner across the various SystemC standards. So a little bit of syntax for callbacks. Here's a parameter owner. This is starting to look pretty familiar. Simple IP module. In the private section, we've got a parameter. It's an integer, P1. Now we've got a callback handle. So this is CCI callback untyped handle. So we indicated that we could be either typed or untyped. We're just specifying that we're interested in addressing this in an untyped way. Giving it a name P1CB. Now then here in the constructor, we're attaching this callback. So we're going to the parameter. We're telling it that we want to register a callback. The specific callback that we want to register is the post-write callback. And when a write happens for P1, we want to call back to our function called CB. And of course it's on this object. So now we've got the callback registered, and anytime that there's a write done to P1, then once it's completed, we'll get a callback into our CB callback method here. And we will get the param write event, and it will have the information that we would want when we were planning to see the details of this particular write. So I think on the next slide we've got the breakdown of what that is. So if we're talking about the write callbacks, this payload consists of handle to the parameter itself, the old value and the new value, and the originator. One of the use cases that we have for the standard, and one of the requirements that we worked with from the beginning, was we wanted the ability to validate values for a parameter. So if your parameter is an integer and the only valid values are 3, 4, and 5, we wanted to have a mechanism to be able to enforce that. So that's what we use the pre-write callback for. So at the pre-write, we could come in here and we can take a look at the new value by the payload attribute. And if it didn't fall into the set of 3, 4, 5, then we can reject that value and the write doesn't happen. Of course, this can be used for preventing write access to a parameter. You can just say, for example, let me look at your originator. If you don't belong in my subsystem or in my module or whatever level of access you wanted to provide, then you could reject the write. Lots of flexibility in what we can do with these callbacks. For symmetry and also to satisfy a requirement, we have the equivalents for read. So if a parameter is about to get read or a parameter has just been read, you can have a callback. And there it gives you not a new value because they're not a value change, but you still get the parameter handle, the value, and the originator. You can see who is accessing your parameter. And then with the broker callbacks, we've got create a parameter and destroy parameter events, and they contain a handle to the parameter that was created or destroyed. And this is pretty capable, this payload that we get with the event. It's the things that we think that you're going to want, but we do have the ability to support a broader set of signatures and interfaces by allowing lambdas and function objects and scbind as well with this callback mechanism. Okay, so a little bit about custom types. First one here is support for legacy parameter implementation is done through the CCI parameter interface. So this is talking about you having a custom parameter type and wanting it to play inside of the CCI standard. And really all that's required above and beyond you satisfying the CCI param if is that you register with the broker at construction. Everything else kind of falls into place if you do those two things. This variant type, the CCI value, provides an extensible infrastructure to specify the adding and unpacking support for custom C++ data types. This is one of the things that we show as in one of our examples. So if you're interested, when we've got the kit available, you can pick it up and play with it. I should mention that for Accelera members, this is already available. And so if you're not in the CCI working group, but you're an Accelera member and you're interested in taking this for a drive before we go public, which is around the corner, let me know, we can arrange that. And then once you have added this support for CCI value with your particular custom data type, then it's going to play well with your CCI param, and it can be used transparently with CCI param as any of the other native supported types do. Okay, to recap what we've seen looking at this bunch of interfaces and some key concepts and a smattering of code, the key message here is that you've seen a lot of things today, but the typical modeler is going to use probably a fairly limited subset of the standard on a routine basis. So when you're picking this up and learning about it, you're probably going to want to be focused on how do I use the parameter to put it into my modules so that it's parameterizable. And then you might, again, want to start looking at, now that we know more about these concepts, if I want to take a look at a parameter in another module, I can use my get broker to get a handle to my broker. I can go to the broker and do a name lookup on a particular name, and that's going to give me a parameter handle. And now then I can use either the typed or the untyped form of the handle to interact with the parameter and read or write its value. We saw the callbacks. That's kind of the next level up. So if you're writing a parameter that's the nature that it needs to be responded to immediately, then within your module you're going to want to create some callbacks, and then when a write happens, you're going to want to go in and respond to that change immediately. Probably, if you're up here in the infrastructure space, there's some callback things that you might want to do at the broker level. If you want to just, for example, report to the user that a new parameter has been created, or you want to report to the user whenever a parameter has been destroyed, then you might want to use the broker callbacks for that kind of information. But again, probably fairly few from the community that are doing that kind of code. And we've talked about and explained the private broker, and that's really more about trying to determine what portions of your configuration information you want to try to lock down and restrict access to and restrict visibility of. And so that's really more about integrating your models and packaging them up and getting ready to send them out the door. And so that's where you're going to be working with and possibly creating a private broker. And then this CCI value converter is really this traits class that takes care for us of being able to take a custom type and pack it into this variant type and vice versa, so that you can add your own user-defined custom types into the picture. And so it's probably more your infrastructure team that's doing a lot of that work. And then there's a bunch of stuff here at the top that we've seen where the tool is going to be interacting with information from the user, whether that's coming from configuration files or it's a user interface, a graphical interface maybe, where we're presenting out information about a parameter like its value and where the value came from, the originator of that value, or the description of the parameter, or the metadata for the parameter. All of that information, is going to be things that you're concerned about when you're kind of up there at that level. So as you pick this up and start playing with it, you probably start down here at the bottom and look at the examples that are relevant to what you're trying to take advantage of and start putting that into your code, and then you start just creeping up the pyramid depending upon what you're wanting to do with the standard. So as we're kind of getting to the close of configuration and looking at getting this thing out the door for public review, we did want to just to mention that out of that big picture I showed in the beginning of all of the pieces that we're looking at to standardize between how the tool at the top level is going to want to get information down at the bottom level from the model. The next things that we're going to work on in this control and inspection space are not completely definitive, but we think that the next thing we want to do is debug for registers. So basically the interface that lets you go into any register implementation. So we're not going to standardize the register itself. Everybody has their own register. We've actually had this discussion as well. You keep your own register class, but we'll put a standard interface on the back door that allows a tool to come in and get the information out of your register and present it to the user. So what's the offset of your register? What's the width of your register? What are the logical bit fields in your register? For each bit field, what's its name and description? What's its size? What are any update policies? Is it write one to clear? Is it read only? All of that information will be incorporated into this interface, and it will allow us to, again, take our models, move them from tool to tool, and make sure that the tool can get that information out of the models and give it to the user to help with debug. So that's probably the thing that we chew on next in this pipeline of things that we have queued up. We think beyond that then is the ability to do checkpointing of models. So that has some implications certainly on the kernel itself, being able to run along to a particular point and have the kernel stop, save off its state, come back a day later and pick up where you left off. But then it also has implication on the models that you are creating as well. So we will come up with a standard for when you're creating your model, how can you make sure that you are getting all of your state stored off and then brought back. There's other things in the queue, but that kind of gives you a preview of the next couple of things that we're going to be looking at. I won't be able to do as an exciting a job as Mike, and probably not as detailed a job as Mike. Winging it here based on a last-minute substitution, but I'll give it my best. So to give it a little bit of background, we have a SystemC TLM evolution working group within Accelera. And the idea there is that we want to take a look at everything that's happening in the SystemC space. So that's analog mixed signal and verification and UVM-SystemC and high-level synthesis and TLM and data types and configuration control and inspection. We look at what is happening and what the roadmap is and where things are going to overlap or interact. And so in the context of that work, I have spent some time looking at UVM-SystemC. So I have a little bit of perspective here that hopefully will allow me to share with you the slides here. So quick outline, why UVM-SystemC, overview of the layered architecture of UVM, the UVM-SystemC LRM and the proof of concept library, status of Accelera standardization, next steps, and a call for help. So why UVM-SystemC? So the current electronic system level focus is on system design, not on verification, and some step up is required. So we all know, we've all seen the graphs, that you really have to spend much more time in the product life cycle doing verification than you do design, and so why not have more of a focus on the verification activities? And the same is certainly true when you're using SystemC as your language for design. So test benches and tests for system design are often ad hoc, unstructured, and incomplete. Of course, UVM helps to address all of that, and there's been this kind of system Verilog bounded UVM swell of capability and advancing the sophistication that we have within the verification domain but it makes a lot of sense to take that and put it into the SystemC context. So no reuse of system verification components and environment, missing link to the RTL world. So again, this kind of structured modular approach that you get from UVM lends itself more easily to being able to reuse components from generation to generation, and because it's really all drawn from or derived from the system Verilog UVM, it links very well. It's a fairly straightforward mapping between the two, and the concepts are spot on, and so you can, from a concept point of view, move between the two, and it's all the same terminology, and it makes a lot of sense. So one of the challenges, of course, so why not just use UVM System Verilog? So it lacks the native C, C++ integration to support software-driven verification use cases. So if you're using SystemC to create virtual platforms and to drive that from a verification point of view with a full software stack or some fairly full software stack, it's difficult to do that, more difficult maybe, or at least not as natural to do that on the System Verilog side. So you can still continue to do that now in your SystemC world, but also have the benefit of UVM. And then we're using test benches and tests and hardware prototyping equipment and hardware in the loop setups. So that's a little bit of why. Okay, the layered architecture. So we got a spec up here. We've got test cases that we write. We've got sequences down here at the next level. Sequencer is taking in the sequences. We've got a scoreboard here that's checking what's happening down here at the device under test and measuring it against the expected results, and it's reporting the results out to our functional coverage tool. And then down here at the command layer, we've got a driver that's taking the sequences and driving them into the DUT. We've got a monitor that, again, is monitoring what's happening, both coming out of the device under test and then also going into the device under test, and then comparing against what we expect here, and then reporting out the results. And of course, these monitors also can just be used to provide some trace of what's happening as well. So if you're at all familiar with UVM, then this is all 100% exactly the same story. Continuation of UVM layered architecture. Top level contains the tests, the DUT, and the interfaces. So top level here are tests are here, stacked up. The DUT's down here at the bottom, and then all the interfaces and the stuff in between. The DUT interfaces are stored in a configuration database used by the UVCs to connect to the DUT. So I don't think that we've got the configuration database shown on the picture here, but it's underlying all of this. Test bench contains the UVM components, the register model, scoreboard, the sequencer to execute the stimulus and check the results. So here we go, tests into the test bench. We've got the sequencer here. In this case, we're showing the detail of a register model. And then down here, we've got a couple of agents. And then each of these agents have this kind of consistent structure that we see in the UVM domain. So a sequencer, a driver, and a monitor, and some configuration component here. So that kind of modularity and that kind of structure is a pattern that we see in lots of places here. And then down here, the note, almost everything is configurable. So there is this configuration database, and it's really it's not existing a priori, so you don't have to think about where does configuration exist when you're creating the modules or the drivers, for example. But you can put this layer kind of on top of the existing components of your UVM system, and then interact with a tremendous amount of flexibility in configuring and deciding how to control what happens in this parameterized way. So standardization status. So this draft 1 happened last year. Seems like it was spring of last year. LRM went out for public review. There was an alpha release of the proof of concept implementation. Since that point in time, the standard is continuing to evolve. In addition to, and in part because of, the feedback that was received during the public review period, there's work now on an abstraction layer for the registers, putting in constrained randomization. So CRAVE is a particular technology that's developed at a university and being incorporated into the standard. There's a focus on the reporting infrastructure and test and regression environment. So the register abstraction layer, here's a quick rundown of the status. So a register model containing registers, bit fields, blocks, etc. It's been developed and it's undergoing testing. Register callbacks are the same status. A register adapter, register sequences, and transaction items are in testing. A register front door access. So front door is basically being able to get at it, I believe, from your sequencer and your driver. Under testing, the built-in register test sequences are under development. The register backdoor access, so HDL path, this is under testing. The memory and the memory allocation manager are under development. Virtual registers and fields are under development, and the randomization of the register content, again going back to the last slide with the randomization and bringing CRAVE into the picture, is a piece that's under development. So you can see much of it's already there and in testing, and those pieces that are in development from following the reflector in this particular working group, they're fairly far along. So a register model example here, class register A, reg A. It's inheriting from UVM reg. This is the UVM register class. And then we've got some bit fields here. So UVM reg field F1 and F2. Reg A now is UVM object name of A, and we're passing on to the initialization of the UVM register the details that it needs, so its name, the size, and in this case UVM no coverage. And then down here in our build, we're building this thing up, so UVM reg field type ID create F1. Back here we got our fields. This is the first field that we created up here. So it's now associated through configuration. So this is still configuration of the field. So we're configuring it to be 8 bits, I think a 0 offset. That's read-write. I'm not entirely sure of all the rest of this, but you can imagine that it's all the interesting detail that you need to configure a particular bit field. And then the same thing for field 2. So again, size and offset and the type of read rules. I think that we've got reset value in here, all the details that you need to configure a particular bit field. Okay, so constrained randomization. UVM-SystemC will introduce this constrained randomization using the CRAVE library. Powerful and extensible constrained random stimuli generator. Leverage the latest constraint solving technologies, C++11 syntax for constraint definition, and more info is available at this link. So I don't recall the specifics. I think this was developed at a university and donated to Accelera, and provides for us the ability now to come in and provide a characterization of what the coverage space is for our UVM components like registers, and then to help us to solve the stimulus that's needed to exercise the DUT in a way that you're getting full coverage in your verification suite. And of course, your vendor is going to provide for you a solution that is fully meeting your needs, but as a stepping stone, this is a capability that's being incorporated into the proof of concept so that you can get started and have something that works, independent of a particular tool. So randomization example, a U-bus transfer, UVM randomized sequence item, Frey variables and vectors up here at the top, read-write enum as read or write. The address is an SE bit vector of 16 bits. The size, presumably, of the data is an unsigned. The data itself is a 8-bit bit vector. The wait state is a 4-bit bit vector. And here are some constraint definitions. So here's a read-write constraint. Here's a size constraint. So this is, I think this is basically saying that the read-write must be either a read or a write. This is saying the size must be either 1, 2, 4, or 8 bits. And this is saying that the weight should be proportional to the size. So the reporting infrastructure for UVM-SystemC, it's upgraded to UVM 1.2 capabilities. It's now object-oriented using the new UVM report message object. All C++ standard output has been replaced by UVM info messages, enabling visibility and verbosity control. So rather than messages always going to standard output, now we have a SC report style control over filtering and redirecting of those messages. For the user, it says no big difference in usage of the API, so it sounds like from the point of view of the interface for reporting information, it's the same. It's just there's now these additional mechanisms that are much more consistent with broader System C for being able to control whether you want to see, just info messages versus warnings versus errors versus fatal, and then also the filtering that allows you to indicate which messages you want to see and which you don't, based upon some reporting ID. UVM report message object extension macros are not yet available. So UVM message add int is an example. Apparently that's something that was requested, possibly through the public review, and that's something that's not there yet. So test and regression environment, simple examples are available in the proof of concept to demonstrate basic functionality. So component instantiation, the factories, doing configuration, reporting and seeing the results, phasing, sequences, etc. You can certainly see that that's all in place with the POC. Unit tests developed as part of a regression suite, closely following the UVM system Verilog tests. So within the working group, the work's done on GitHub, and so there's a separate repository for the regression. So presumably this is going to be released, and it may already have been with the public review last time, I'm not positive. But it's a suite of tests that you can run just to make sure that your installation is working properly, and of course then as you make any changes, that everything is still working. More integrated examples are under development, so the example here is the U-bus and the codec example. So presumably those are going to be available with the next official release of UVM-SystemC, and currently adding new unit tests for the register model testing. So as the new capabilities and features are being added, there's corresponding sets of tests that are going into this regression repo. Those are going to be available as well. So I guess the bottom line is that there's a good starting point there for regression testing, and it's being updated as the standard is evolving. So next steps on UVM-SystemC, update the LRM. So the pieces that have been added that need to be reflected within the LRM are this register abstraction class, of reporting classes, this constrained randomization API and functional coverage. So certainly there will be all the detail about what you can do with that crave under the hood. Introduction of UVM-SystemC and Accelera multi-language verification standardization. So the multi-language working group is working on how to create a backplane for all of these various languages that come into play when we are describing and verifying our systems today. And so this is being introduced into that space. And then aligning configuration concept with the System C CCI working group. So we have had a number of exchanges between the two working groups around configuration, and we're working to try to align at least concepts as much as possible, and then also to make a very well understood prescription for how you go about and when you go about using the configuration facilities in UVM-SystemC, which are very much the same and inherited from UVM-System Verilog, and then when you would want to use the configuration control and inspection configuration component that's being developed in the CCI space. And then, of course, the call for help. So there's lots going on here. Like I said, I do subscribe to the reflector for this working group. I can see that there's a lot of activity happening within the GitHub repo and a lot of conversation that's happening on the reflector for the working group. There's regular meetings. You can jump into the middle of that and contribute. So if you're not yet a member organization, try to convince the powers that be at your company to get a membership. There's 2 levels there. Become a member, and then once your company is a member, then any employee in the company can create an Accelera account and join into any number of working groups. And there's lots of help that's needed there. So some examples here are developing the unit tests, and of course you can certainly bring your own perspective into that work. So if you've got particularly unique requirements or something that you want to see illustrated, this is an awesome opportunity to come in and to create those tests in a way that addresses those needs and perspectives. As well, there's this mention of having more real-world, slightly bigger than these unit tests examples, and so you can contribute to those or come up with your own. The more, obviously, of that work that can be done, the better tested this is, and the more confidence that we have that it's going to work broadly, all the way up to full applications. In addition to that, even you can contribute to the proof of concept itself. So there is this incremental work that's happening. You can jump in and take a piece of that. But aside from that, you can also come in and look at improving the robustness of the code that's there, the quality, the maturity, contribute in any way to help with the software lifecycle of the proof of concept.